CO2, which is nowadays standard, or you can say this is still a barrier. We are not able to design the unit for less than this number, which is around 1.4 kg steam per kg of CO2. The cooling duty is approximately 62 gigacal per hour. The towers. This equipment are very powerful towers. Basically, diameter is less and height is very large. So we call them towers. I'm going to present you how they look like for this particular case. The flue gas sponge tower, which is the very first equipment, 2 towers are required. Each is having a diameter approximately 14 meter and height 28 meter. This is approximately 14 meter in diameter and 28 meter height. Then the next equipment, big equipment, is a exhaustion tower. There are 2 exhaustion towers required, and each is having a diameter 14 meter, height is 15 meter, and only one steeper is required. The diameter is 10 meter and height is around 38 meter. So these are 2 towers. This is 1 tower, with 14 meter diameter, 50 meter height. This is approximately 10 meter diameter, height is 38 meter. Okay, this as far as the tall towers or big equipments are concerned. Then how much is the heat duty required? The heat duty for steeper revolver is around 249 gigacal per hour, and total power is this is basically coming from the previous slide, 16 megawatt. Cooling water, which is required, is around 36,000 meter cube per hour. These are the net utilities required for this process: steam, power, and cooling water. And in terms of the chemicals, we need a solvent, which is 220 kg per hour, which is continuous requirement. Caustic soda to be SOx removal, 3.2 tons per hour. Then there is sodium carbonate for SOx removal and reclaiming purpose, around 2.1 ton. Then activated carbon, which is used as a filtering medium for solvent. It's around 1,340 meter cube per batch, and batch is approximately 6 months. Every 6 months, you need to replace 1 batch. So these are the total chemicals which are required for this carbon capture facilities. And what are we going to discharge from this unit? Basically wastewater, then reclaimer waste, then spent activated carbon, which are to be thrown to wastewater. Normally goes to sea or for wastewater treatment purpose. Then reclaimer waste is normally we have no option except either go for the incineration purpose or go for the landfill. And spent activated carbon is normally go for landfill purpose. Now, the chemical cost. It's basically, if you remember one of this slide, I showed you these are the base data for the utilities, and this US dollars per annum. The cost on account of utilities is around $22 million per year, and operating and maintenance cost is around 32.4 million tons per year. How do we calculate the operating and maintenance cost? It's basically 3% or 4% of the capex. The normally, which is pretty standard, 3 to 4% of capital expenditure. So total OPEX comes $76.4 million, and the capital expenditure, which we estimated around 2 years ago for these equipment, was $728 million US, and the equipment cost for this was 170 million, and total investment cost, which includes all materials, piping, electrical, civil, and all project costs, various project sites, gets built up to $728 million US dollars. This is the cost data. Now, how this looks like? So we were talking about the plot which is available. This is the plot which has been used. Say, is whatever you see here, this is a power plant facilities. I will show you. And this area is the area which was located or identified for carbon capture facilities. These are all real data. And this slide shows only the additional carbon capture facilities. These are two time points, one for one HRSG, second for second HRSG, coming to the pulse tower. From pulse tower it's going to the absorption tower. The absorption tower to steeper. Then there is a compressor. This side we see the stack. And at the far away we saw basically this unit is having a 4 GTs operating continuously and 2 GTs standby. And those 2 GTs which are standby are without HRSG, a single cycle, not a combined cycle. Since the power requirement increased, so one of the GTs we require to make it a combined cycle. So additional HRSG was installed. And then since we need a low pressure steam, and the steam which is produced in the power plant is a high pressure around 75 bar. So one steam turbine was designed which will produce the power, and the low pressure steam will be used for the regenerative purpose. So this slide shows all the new facilities. It's basically, if you want to make a power plant CCS ready, these are the facilities which are required. So what are the, yes please?
Does we really require a stack?
And?
Stack.
Yes, we need a stack. What for is required? Say, normally this is stack, there is no effluent from this stack. Whenever there is a startup, shutdown on a stack, off a stack, the CO2 which is produced, we are not able to pump it to the pipeline. It is office space, or there is some depressurization to be carried out. At that time, this CO2 is to be released to the atmosphere. So this is some sort of cold vent. So whenever there is a requirement to depressurization or for the office part and to stabilize the unit, at that time the CO2 or any other effluent can be discharged to this system. This is normally it is not having any emissions. The emissions, continuous emissions, are only from this towers.
Because the flue gas is actually recirculated, so that oxygen combustion.
This is a post-combustion, so just let me understand your question. Retrofitting based on the post-combustion technology. So, in one of the slides, I will go back to you. So this is based on this configuration. So there is a absorption tower, there is a pulse tower, there is a steeper tower. The retrofitting today is feasible or practical, or somebody can estimate only with respect to this post-combustion. Any other question on this? Okay, we go to the next one then. This gives an idea what are the new this is one new piece of equipment, and here there is one new piece of equipment. This is a steam turbine, this is HRSG, and these are the stacks. If you see from the power plant, these with HRSG are operating, and these HRSGs having a provision of duct firing. And normally, duct firing is zero, there is no CCS. When you put up CCS with some duct firing, it can provide you the sufficient steam and sufficient power. But what happens when you are operating the duct firing, the availability reduces. And this was not acceptable from the RAM study point of view. And the availability reduced to less than a critical number. Normally, for this plant, RAM needs around 99.8% availability. When we have a duct firing, without duct firing, because duct firing is not there, it was meeting the availability criteria. But with the duct firing, it reduced. When it reduced, to increase the availability, those standby GTs require one HRSG. So to answer the question, normally this is not required to operate with CCS. But if one of the GTs is down, at that time this needs to be in operation. And the steam turbine is basically getting the steam from whichever four GT with HRSG are in operation. Whether these four, there is one more from the opposite side. This again review from different sides to show you how it looks like. And before I go to conclusion on this subject, any question on these slides? Because this is the hard data. This
power consumption, as you said, about 16.2 megawatts, right, for CCS plant. What is the capacity of CO2 for this?
2.4.
It is for 2.4 million
tons
per annum. That's 16.2 megawatts. What is said for per hour? All the blowers and all the pumps will have to continuously be running. Yes. And what is the capacity per hour you can able to collect as a CO2?
I'm not
No. There is almost a quantity of CO2 per hour collection.
Per
hour.
Per hour.
Okay. See, you have to run the plant for 16.2 megawatt. That is continuously consumed, right? And what is the quantity of CO2 collected at per hour?
Per hour. Okay, this is approximately, not, I don't have a calculator, approximately 7,000 tons per day. And it is 7,000 tons per day divided by 24, approximately. Okay, but you can calculate it by, say, working hours we are taking around 8,400.
This is 16.2. Normally the 210 megawatt boiler which is running here. The actually power consumption itself comes about 14 megawatts. So approximately 7.8 to 8%. Suppose if the mandatory is going to be there, and if you introduce the CCS plant, so 15% is the auxiliary power.
Yeah, the simple arithmetic calculation. So this is only base data with respect to, that's why you give out CO2. Say the carbon capture cost, OPEX and CAPEX are directly proportional to CO2 quantity. CO2 to be recovered. So from a coal-based power plant, it will say in the base data it should be around 7% CO2. But a power plant which is coal-based will have much more CO2. So accordingly one can apply this data judiciously.
Okay.
This cost, I made it very clear, is only for carbon capture facilities, which is if something is required for fuel desulfurization or denitrification or something else, those are the additional costs. Even I mentioned it, it doesn't.
From the environmental point of view, very separate.
Yes.
From the capture from the sequestration point of view, you said 7.8.
Okay. That's a good question. Say, in this, I consider what is the sulfur content, I consider around 133 ppm. Okay, for that purpose, then in one of the slides I said the caustic soda. Okay, let us go to hard. So here, if you see, this is considered 133 ppm. So the sulfur removal is required. Okay. I mentioned during my discussion that normally 133 is the gas based and gas does not have any sulfur. So in this slide, we show you this caustic soda for soft removal around 3,200. So this has been considered. Pardon?
Oxygen and the NOx control factor. Other places.
Okay. SOx we have considered it. For the NOx, say NOx was here 59 ppm. For this 59 ppm, no additional denitrification facilities were required. Okay. The 59 ppm is obtained after having a low NOx burner in this GT side. So once we have 59 ppm of NOx, which are acceptable to the process, and no additional facilities are required for this purpose. And then we come to the oxygen purpose. So the oxygen here is approximately 11.2% of the flue gas, and in the product we need only 150 ppm of. So we don't need any additional facilities because these solvents are very selective for CO2. The solvents reject oxygen along with nitrogen. They are very, that solvent has an agility only for the polar components. CO2 being a polar component, it gets accepted along with the solvent, and O2 and others are removed via flue gases. Like if you see here, exit gases, nitrogen and oxygen which is present there is rejected by this route. So no oxygen is controlled. When we go to the next stage, which is a compressor. Say this CO2. This CO2 which is produced at the top of the steeper column is saturated with water, and once it is available at an atmospheric pressure, approximately 1.2-1.3 bar pressure, then it goes to the compressor. When it goes to the compressor, when you are increasing the pressure, the water gets condensed out. So it is approximately 7-stage compressor which is required to increase the pressure from atmospheric to 230 bar, and in this so this steam is saturated with water. This does not have conductivity, but this will ultimately go to the what is the compressor? There is a first compressor, then there is a cooler, there is interstage cooler, then there is interstage knockout drum, then the next stage. When you go to the interstage knockout drum, there this water starts condensing out. And in various stages, it's possible you can come to this level, and therefore how the condensation takes place, how the compression takes place, how we divide the various stages. If we are not able to meet that, then in one of the two, maybe third stage or between third compressor stage and fourth compressor, we can put this dehydration unit, which is a small unit, either it is solely adsorbent based or maybe some other type. But it is not, you are right, it is not controlled by this. This does not include, that will be included as part of compressor. With this, if you don't have any other question, our general conclusions are that flue gas desulfurization, denitrification technologies are mature, clean coal technologies. CCS technology for the large economy is still in a development stage. Presently, there is no clear CCS technology winner, which is general conclusion. And application of CCS in power sector for technology demonstration purpose is highly desired. HS issues related to CCS need to be addressed adequately. With this, I complete my talk on CCT and CCS. And if you have any question on this subject, we can take it now. Otherwise, I will present something on the oxy-fuel technology. Health, safety, and environmental issues. Health, safety, and environment.